Today I'll be discussing the Maclaurin series and how to find the Maclaurin series of a function from the known Maclaurin series, which are the ones given below, and I'll show you how to find radius and interval of convergence. This topic is actually really interesting and it's one of my favorites. The known Maclaurin series can be deduced from the Taylor series at the point 0. By that I mean when a is equal to 0. I've prepared these 3 questions which we'll be working on today. First, to show that arctangent x is that given series, we'll make the use of geometric series. We start by taking f of x equal to arctangent x, and we compute the derivative of f of x, which is the derivative of arctangent x, which is equal to 1 over 1 plus x squared. We need to bring this to the form of geometric series, which I've written above, which is 1 over 1 minus x. So in the denominator, we should have 1 minus something, right? I'll just copy it down and put it here to look and compare. We also know that the radius of convergence is equal to 1, which will make sense by the end of the video where I explain how we find it and what that really means. So now we need to just adjust our answer, the derivative of f of x, so that we have something similar. So the denominator now is 1 minus x squared, which as you see didn't change 1 plus x squared because of minus, but now we have what we needed. We have 1 minus something in the denominator. Now we'll just equal it to the series from 0 to infinity of minus x squared to the power of n. And this equals to sum from 0 to infinity of minus 1 to the power of n times x to n. It is absolutely important to write for which x this holds. In our case, it is the absolute value of minus x squared less than 1. It's because of the radius of convergence of the geometric series that we used. In that case, in the case of geometric series, is the absolute value of x less than 1, because there we have x to the power of n. And in our case, we have minus x squared inside the series that's then taken to a power of n. So it logically makes sense. If you compare these two series, you know for which x this holds. Now I'm just rewriting it to bring just the x there, and if we just rewrite it, we again get the absolute value of x less than 1, which means the radius of convergence of arctangent is also 1, which I'll demonstrate right now. To do that, we take the integral from 0 to x of arctangent t, it could be any variable, and which is equal to the sum from 0 to infinity of minus 1 to the power of n times the integral from 0 to x of t to the power of 2n dt, and we just compute it. In the left hand side we get arctangent x by the fundamental theory of calculus part 1, and the left hand side we get sum from 0 to infinity of minus 1 to the power of n times t to the power of 2n plus 1 over 2n plus 1 computed at 0 to x. And this is equivalent to arctangent x, which is equal to sum from 0 to infinity of minus 1 to the power of n times x to the power of 2n plus 1 over 2n plus 1. Of course, we don't forget to write for which x. Here it's for all x in the absolute value less than 1. Let's move to the next question. We have to find the Maclaurin series for the given function. There are multiple ways of solving this. Today I'll show how to do it by the use of geometric, arctangent x, and binomial Maclaurin series. First, I'll start by doing the geometric series. I just rewrite this function just as we did before to prove that arctangent x is the series that is given. So we get x to the power of 5 times sum from 0 to infinity of minus x squared to the power of n, which is equal to x to the power of 5 times sum from 0 to infinity of minus 1 to the power of n times x to the power of 2n, which is equal to, we have to just combine the powers of x. We have sum from 0 to infinity of minus 1 to the power of n of x to the power of 2n plus 5. And of course, we have to mention for which x. Here we have the absolute value of minus x squared less than 1, which is just the absolute value of x less than 1. Next, we'll do it by the use of arctangent x Maclaurin series. And here, as soon as we look at it, we see the derivative of arctangent, which is 1 over 1 plus x squared. Remember that. You have to see it or rewrite a function if you want to use arctangent x. So in this case, we get x to the power of 5 times the series from 0 to infinity of minus 1 to the power of n times x to the power of 2n plus 1 over 2n plus 1 derivative. So we need the derivative of that series. So we get x to the power of 5 times, we just derivate the inside part of the series. So we just have 2n plus 1 and 2n plus 1 that cancel on both of the numerator and denominator. And we simply have x to the power of 5 times sum from 0 to infinity of minus 1 to the power of n of x to the power of 2n. And by the way, guys, I had to edit minus 1 to the power of n in the video because I was so tired I forgot to put n there. And of course, we again mention for which x, and here is for all x in the absolute value less than 1. And as you see, we get the same answer as we should, because otherwise it means there's something wrong with our answer. Let's move to binomial Maclaurin series. I just rewrite that part with the power, which is just minus 1. And we keep in mind that that's k. We have x to the power of 5 times, we just arrange the binomial Maclaurin series to this. We have minus 1 n and x to the power of 2 times n, just 2n. And now we just have to expand the coefficient. In most of the binomial Maclaurin series, like if you use it, then you try and expand the coefficient. If it can be expanded, you just write it neatly. Actually, you could keep it like this, I believe, but it's better if you rewrite it, and then you'll see that you'll come to the same answer as we did with other methods. And yeah, so the coefficient here is just k times k minus 1, k minus 2, all the way to k minus n plus 1 over n factorial. So we just rewrite it for the k's that we have, which is minus 1 instead of k. After writing it out, we just see a pattern, which is minus 1 times minus 2 times minus 3, all the way to minus n over n factorial. And we can just take the minus 1 to the power of n out, and at the top we have n factorial, and in the denominator we still have the n factorial. We will just cancel it out, and it means our coefficient is just -1 to the power of n. Back to our Maclaurin series, we have x to the power of 5 times, we just rewrite this, where instead of the coefficient we write -1 to the power of n. Lastly, by just combining the powers of x, we get our final answer. For all x in the absolute value less than 1. Again, warning, don't forget it. We students always forget it, and it's just a headache later. And finally, the last exercise of today is to determine the radius and interval of convergence of the following power series. Today I'll show you that finding the radius of convergence can be done in two ways. First is the formula r is equal to limit as n tends to infinity of absolute value of Cn over Cn plus 1. Here Cn is the coefficient. Or the second way is by the ratio test. Whenever we do the ratio test, we'll need an additional step to determine the radius of convergence, because the answer we get, we have to say that it's less than 1, otherwise it will not converge. Because the ratio test states that if that following limit, that n tends to infinity of an plus 1 over an in absolute value, if it's less than 1, then the series is absolutely convergent, which implies it's convergent. First, I'll do it by the ratio test. In both of these exercises, I'll show both of the ways of finding radius of convergence, but you don't have to do that in the exam unless it states so. You have to just use one of them. It's just two alternative ways. So first I'm doing it by the ratio test, and in this case we have this whole thing, but instead of n we just write n plus 1, and which is just square root of n plus 1 over 8 to the power of n plus 1, and then we just write the x plus 6 to the power of n plus 1, and then times. Because it's division, I like to write times, but then obviously you don't have to forget to flip the fraction. And here we don't know whether x is positive or negative, that's why we can't get rid of the absolute sign. But in some exercises it states that it's positive, and as we know that n tends to positive infinity, we can get rid of the absolute sign, but not in this case. Here I just cancel out what is possible to cancel out, and I just rewrite what is left. In this case we have 1 over 8 times the absolute value of x plus 6 times the limit as n tends to infinity of n plus 1 over n in the square root. And actually, I'm not saying you should remember, but you should definitely know if you do enough math that this limit is just 1. We see this a lot, so it's useful to remember it. But here, just to demonstrate it by the limit laws, I'll rewrite it for the ones who don't straightforwardly see it. So this equals 1 over 8 times the absolute value of x plus 6 times, we'll take the square root, so like the limit inside the square root, because square root is a continuous function. And here I'll just change the variable. So we have limit y tends to infinity of 1 plus 1 over y over 1, and by the limit laws is just 1 over 8 times the absolute value of x plus 6. And we have that it's less than 1 because we are doing the ratio test, remember? And we just have to multiply both sides by 8. We get absolute value of x plus 6 less than 8. This implies that our radius of convergence is just 8. Now let's do it by the second way, which is r is equal to limit as n tends to infinity of cn over cn plus 1. Again, I forgot to write limit as n tends to infinity before, so just ignore that, please. So we just continue by writing limit n tends to infinity, absolute value of square root of n over 8 to the power of n times, we flip the fraction 8 to the power of n plus 1 over square root of n plus 1. We can cancel the absolute value here because n is tending to positive infinity. Also cancel the powers of 8, we get 8 times limit as n tends to infinity of under the square root n over n plus 1, which is just 1. So the answer is 8. If you get two different answers for two different ways of finding the radius of convergence, then it means you have done a mistake somewhere. There has been an error because they should equal. So we have the absolute value x plus 6 is less than 8, which is equivalent to x plus 6 is greater than minus 8 and less than 8, which is also equivalent to x less than minus 14 and x being greater than 2. So these are our boundary points, and we'll see whether the series converges or diverges at these points. And based on that, we'll determine whether these boundaries are included in the interval of convergence. So let's start by taking x minus 14. It means that x plus 6 will be equal to minus 8, and we put it to our series from 1 to infinity of square root of n over 8 to the power of n times minus 8 to the power of n. Here we just cancel out. So we have our series from 1 to infinity of minus 1 to the power of n times square root of n. We take the limit as n tends to infinity to check whether the limit exists, whether it's equal to 0 or it doesn't. So in this case, we see that it doesn't exist by the test for divergence. We have the series is from a 1 to infinity of square root of n of minus 1 to the power of n is divergent. It means that our point minus 14 is not included in the interval of convergence. Now let's check the point at x being equal to 2. We have x plus 6 equal to 8, which means our series is from a 1 to infinity of square root of n over 8 to the power of n times 8 to the power of n, which is equal to, we just cancel it out, which is equal to sum from 1 to infinity of square root of n. And we take the limit as n tends to infinity. We have square root of n equal to infinity, which means by the test for divergence, the series is divergent. Again, that means this point is also not within the interval of convergence. So we write I is equal to, which is interval of divergence, open brackets from minus 14 to 2. Both sides are opened because none of the points are included within the interval of convergence. For the next example, I decided to show finding the radius of convergence in two different ways again, and to use the method where we take the coefficient, we'll need to do some adjustments because here it's not in the standard form. So I've just prepared it already to avoid too much writing. We just need to take out x and have our a. In this case, a is 4/5, and our coefficient is 5n over n to the power of 3. And we just do the usual. We have 5 to the power of n over n to the power of 3 multiplied by n plus 1 to the power of 3 over 5n plus 1. Can get rid of the absolute value again because n is tending to positive infinity, and we can also cancel out the terms that is possible to cancel out. We get 1/5 times limit as n tends to infinity of n plus 1 over n cubed. We did this so many times, we know that that is just 1. So our radius of convergence is 1/5. The alternative way of doing it is by the ratio test. Here we'll take an additional step, which you'll see by the end of this video. So we have limit as n tends to infinity of absolute value an plus 1 over an, which means the whole thing. So we have limit as n tends to infinity, absolute value of 5x plus 4 to the power of n plus 1 over n plus 1 to the power of 3 times n to the power of 3, 5x plus 4 to the power of n. So we just again cancel out, find the limit. So here we cancel out the power of 5x minus 4. So we're just left with the absolute value of 5x plus 4 times the limit as n tends to infinity of n over n plus 1 cubed, which we know is 1. So this is equal to absolute value of 5x minus 4. But we're not done yet. We still need to make it less than 1 and then find the radius of convergence. So you could do this directly, but I wrote it out. So we have 5x minus 4 greater than minus 1 and smaller than 1, which makes our x greater than 3/5 and smaller than 1. So the radius of convergence will now be 1 minus 3/5 divided by 2, which is 1/5. As you see, it's the same as before. All there is left to do is to check the boundary points to be able to find the interval of convergence. So we first take x as 3/5, and here I was supposed to draw a implication sign. I don't know why I put an equal sign there. As I say, it was like so late. So here we get alternating p-series test, which is absolutely convergent. And you know what that implies? It implies that it is also convergent. So here, as you see, p is just 3, which is greater than 1. That's why this whole series is convergent, which means this point will be included in the interval of convergence. We check the second point, which is 1, and in this case we have our sigma from 1 to infinity of 1 over n cubed, which is a p-series with p greater than 1, where p is just 3, which also means it is convergent. So both of the points will be included in the interval of convergence, which I'll write down now. And as you see, this implies that the interval of convergence is equal to closed brackets from 3 over 5 to 1. And finally, we're done. This was a long video. I hope this video was useful for you and that you learned a lot. I hope this made your studying a lot easier. So please subscribe to my channel and put likes and give me some video suggestions in the comments. I'll try my best to make a video.